Welcome. Today's problem is LeetCode number 427, Construct Quad Tree. In this problem, we'll explore how to efficiently convert a 2D grid of binary values into a quad tree representation. Get ready to dive into the world of recursive data structures and learn some interesting concepts along the way. In this problem, we are working with a data structure known as a quad tree. A quad tree is a type of tree where each internal node has 4 children, and it's commonly used to represent two-dimensional spaces by recursively dividing them into 4 quadrants. Here, your task is to construct a quad tree from an nxn binary matrix, where each cell in the matrix contains either a 0 or a 1. The purpose of the quad tree in this context is to compress the matrix into a more compact form. Each node in the quad tree has several attributes: val, which represents the value of the node and is meaningful only for leaf nodes, isLeaf, which tells us if the node is a leaf node, and top left, top right, bottom left, and bottom right, which are references to the 4 child nodes. For leaf nodes, these references will be null. The construction follows specific rules. If all the values in a region of the matrix are identical, that region is represented as a leaf node with val set to true if the values are all 1s, and false otherwise. This representation allows us to effectively compress uniform regions of the matrix into a single node. If, on the other hand, the values in a region are not uniform, the region is divided into 4 equal quadrants: the top left, top right, bottom left, and bottom right. In this case, a non-leaf node is created with isLeaf set to false, and it will have references to the 4 child nodes representing the quadrants. To solve the problem, you need to implement the function construct grid, which takes as input a 2D binary matrix of size nxn. Here, n is guaranteed to be a power of 2, and it ranges from 1 to 64. The function should return the root node of the constructed quad tree. The input is a grid where each cell contains either 0 or 1. The output quad tree should represent the binary matrix in its compressed form. Let's explore some examples to clarify how this construction works. In the first example, the input grid is a 2 by 2 matrix, 0, 1, 1, 0. Since the grid is not uniform, the root node of the quad tree is a non-leaf node with isLeaf set to false. It has 4 children, each representing 1 quadrant of the grid. For the top left quadrant, the value is 0, so it's a leaf node with val equals false. For the top right quadrant, the value is 1, so it's a leaf node with val equals true. Similarly, the bottom left quadrant is a leaf node with val equals true, and the bottom right quadrant is a leaf node with val equals false. This demonstrates how non-uniform regions are divided into smaller parts, with leaf nodes created for uniform subregions. In the second example, the input grid is another 2 by 2 matrix, 1, 1, 1, 1. Here, the entire grid is uniform, as all the values are 1. As a result, the quad tree consists of a single node, which is a leaf node. This node has val equals true and isLeaf equals true, indicating that the entire region can be represented as a single compressed node. This example highlights how uniform regions of the grid are directly represented as leaf nodes without further subdivision. In the third example, the input grid is a 4 by 4 matrix, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1. The grid as a whole is not uniform, so the root node is a non-leaf node with isLeaf equals false. The grid is divided into 4 quadrants. The top left quadrant contains all 1s, so it's a leaf node with val equals true. The top right quadrant contains all 0s, so it's a leaf node with val equals false. Similarly, the bottom left quadrant is a leaf node with val equals false, and the bottom right quadrant is a leaf node with val equals true. This example demonstrates how larger grids are recursively divided into smaller quadrants, with leaf nodes representing uniform regions. The constraints and edge cases for this problem ensure that the solution is both efficient and robust. The grid will always have dimensions nxn, where n is a power of 2, such as 1, 2, 4, 8, up to 64. Each cell in the grid contains either a 0 or a 1. The quad tree must compress the grid as much as possible, minimizing the number of nodes. Some notable edge cases include a grid that is entirely uniform, where the result is a single leaf node, and a grid with the smallest possible size, n equals 1, which also results in a single node. For the largest possible size of n equals 64, the solution must handle the input efficiently without excessive computation. This thorough consideration of constraints and edge cases ensures that your implementation will be both accurate and scalable. To solve the problem of constructing a quad tree from a 2D binary grid, there are several approaches we can consider. The quad tree structure is recursive by nature, where each node represents a subregion of the grid. These nodes can either be leaf nodes, if all values in the subregion are uniform, or internal nodes, if the region contains mixed values. One intuitive method is the brute force divide and conquer approach. Here, we recursively divide the grid into 4 quadrants. For each quadrant, we check whether all the values in that region are the same. If the values are uniform, all zeros or all ones, we create a leaf node. If the values are mixed, we further subdivide the region into 4 smaller quadrants and repeat this process recursively. This method mirrors the hierarchical nature of the quad tree, making it a straightforward way to approach the problem initially. The brute force divide and conquer approach can be broken down into a series of steps. First, we define a recursive function that takes the current grid region and its bounds as inputs. This function checks if the region is uniform. If all values are the same, we create and return a leaf node. If the region contains mixed values, we calculate midpoints to split it into 4 subregions. For each of these subregions, we recursively construct child nodes and return a parent node that links these children. While this approach is conceptually simple, its efficiency is worth examining. The time complexity is n squared asterisk log n, where n is the grid size. This arises from scanning all values in smaller and smaller subregions. Additionally, the space complexity is log n due to the recursion stack depth. However, one significant drawback is the repeated scanning of the same regions, which leads to redundant computations. This inefficiency makes the brute force approach less suitable for larger grids, especially when dealing with sparse data. To address the inefficiencies of the brute force method, we can adopt an optimized approach that uses pre-computation with memoization. The key insight here is to avoid redundant scans by pre-computing prefix sums for the grid. This technique leverages the inclusion-exclusion principle to quickly calculate the sum of any subregion. With this optimization, we can determine if a region is uniform in constant time, significantly improving the process. The steps involve first constructing a prefix sum grid, where each cell holds the cumulative sum of grid values from the top left corner to that cell. Then, for any given subregion, we use the prefix sum grid to compute the sum of values in constant time. If the sum equals the area of the region, indicating all ones, or if it is 0, meaning all zeros, we create a leaf node. Otherwise, we proceed with a recursive division into quadrants, similar to the brute force approach. The overall time complexity remains n squared asterisk log n for constructing the quad tree, but this method is faster in practice due to the elimination of redundant checks. The space complexity increases to n squared to store the prefix sum grid, but this trade-off is worthwhile for the performance gains. While the optimized divide and conquer method reduces redundant computations, it does come with some trade-offs. The use of a prefix sum grid requires additional memory, and there is an initial overhead in computing the prefix sums. However, this extra effort is justified for larger grids, where the performance improvement becomes significant. Another alternative is to simulate the quad tree construction iteratively instead of using recursion. Although this is theoretically possible, it is less intuitive and considerably more complex to implement. For this reason, iterative simulation is not commonly used for this problem. Among the approaches discussed, the optimized divide and conquer strategy with prefix sum stands out as the most practical solution. It strikes a balance between clarity, efficiency, and scalability, making it well-suited for handling both uniform and non-uniform grids. While the brute force method is easier to implement, it struggles with performance on larger or sparse grids. Iterative simulation, on the other hand, adds unnecessary complexity without significant benefits. When comparing these approaches, we see clear trade-offs. The brute force divide and conquer approach is simple to implement but inefficient for large grids due to redundant computations. The optimized approach, while slightly more complex, is far more efficient for larger inputs, thanks to the use of prefix sums. Iterative simulation is avoided because of its added complexity and lack of meaningful advantages. The key insight, or aha moment, in this problem lies in recognizing its recursive nature, which aligns perfectly with a divide-and-conquer strategy. The use of prefix sums to detect uniform regions in constant time is the critical optimization, enabling us to handle both uniform and non-uniform grids effectively. Additionally, the quad tree representation itself is space-efficient, as it avoids storing redundant data for uniform regions. By leveraging these insights, we arrive at an elegant and efficient solution that performs well across a variety of scenarios. The problem we are solving is to construct a quad tree from a 2D grid of binary values, which are either zeros or ones. A quad tree is a hierarchical data structure where each node represents a square region of the grid. If all values within the square are the same, either all zeros or all ones, the node is classified as a leaf node. Leaf nodes contain the value of their region and do not have any child nodes. On the other hand, if the values in the region are not uniform, the node becomes an internal node. This internal node divides its region into 4 quadrants, which are represented as child nodes, and the process continues recursively for each quadrant. To implement this, we start by ensuring the input grid is valid, meaning it is a 2D list of binary values and its dimensions are a power of 2, as quad trees require square grids with dimensions like 2 by 2, 4 by 4, or 8 by 8. Next, we define the structure of a quad tree node. Each node has attributes to store the value of the region, whether the node is a leaf, and references to its 4 child nodes. For leaf nodes, these child references will simply be none. Once the node structure is defined, the main part of the algorithm is a recursive function called construct. This function takes 3 parameters, the coordinates of the top left corner of the current region, x, y, and the size of the region, length. The base case of the recursion is when the region size is reduced to 1, meaning we are looking at a single cell in the grid. In this case, we create and return a leaf node with its value set to the binary value at that cell. If the region is larger than a single cell, we need to determine whether all values in the region are the same. To do this, we iterate through the cells of the region to check for uniformity. If the region is uniform, we create a leaf node with its value set to the common value of the region and mark it as a leaf. However, if the region contains both zeros and ones, we divide it into 4 smaller quadrants. Each quadrant is processed recursively using the construct function, with updated coordinates and dimensions. The top left quadrant starts from x, y, the top right from x, y plus length /2, the bottom left from x plus length /2, y, and the bottom right from x plus length /2, y plus length /2. The results from these recursive calls are combined into an internal node which is not a leaf, and its child node references are set to the results of the 4 quadrants. After defining the recursive logic, the final step is to call the construct function on the entire grid. This is done by passing the top left corner of the grid, which is 0, 0, and the grid size, n, to the function. The resulting node from this initial call becomes the root node of the quad tree, representing the entire grid. The algorithm follows a divide-and-conquer strategy, where the grid is divided into smaller subregions, and the process is repeated until each region is either uniform or a single cell. To optimize the uniformity check, we can use a single loop to verify uniformity and compute additional metrics like the sum of values, if needed, to reduce redundant calculations. One major advantage of this approach is memory efficiency. By using leaf nodes to represent uniform regions, we avoid storing redundant data for large areas of the grid that have the same value. Additionally, the quad tree structure itself is efficient for representing hierarchical spatial data. The recursive nature of the algorithm is managed using the function call stack, which keeps track of state as the algorithm processes smaller and smaller subregions. Analyzing the complexity of this algorithm, the time complexity is determined by how many times we divide the grid and process its cells. In the worst-case scenario, where the grid is completely non-uniform, every level of recursion divides the grid into 4 subregions, and we visit all cells at each level. This results in a time complexity of O(n squared), which is equivalent to iterating through all cells in the grid. For space complexity, the recursion stack requires space proportional to the depth of the quad tree. Since the grid size decreases by half with each level of recursion, the depth of the tree is log n, giving a space complexity of O log n. When implementing this algorithm, there are a few edge cases to consider. For example, if the grid is completely uniform, containing only zeros or ones, the output should be a single leaf node representing the entire grid. For the smallest possible grid, which is 1 times 1, the algorithm should immediately return a leaf node without any further recursion. On the other end of the spectrum, the algorithm should also handle large grids, such as 2 to the power of 10 x 2 to the power of 10, efficiently within the given time and space constraints. These considerations ensure the algorithm is robust and performs well across all input scenarios. Here, we start by defining the node class, which represents the structure of each node in our quad tree. Each node has a value, val, which indicates whether the region it represents is entirely filled with ones or zeros. The isLeaf attribute tells us if the node is a leaf node, meaning it represents a uniform region of the grid. Additionally, the node has 4 child pointers, top left, top right, and bottom right, which connect to the corresponding subregions of the grid. Next, we define the solution class and its construct method. This method takes the input grid and builds the quad tree. Inside construct, we define a helper function, isUniform, which checks if a subregion of the grid is uniform, meaning all cells have the same value. It returns a tuple, a boolean indicating if the region is uniform, and the value of the cells if it is. This function is key to determining whether we create a single leaf node or need to continue dividing the grid further. Another helper function, buildQuadTree, is designed to recursively construct the quad tree. If the size of the current region is 1, it creates a leaf node directly, as a single cell is always uniform. Otherwise, it first checks if the entire region is uniform using isUniform. If it is, we create a leaf node with the appropriate value. If not, we proceed to divide the grid further. To divide the grid into smaller subregions, we calculate half, which is half the size of the current region. We then recursively build the quad tree for the top left, top right, and bottom right subregions using the buildQuadTree function. For each subregion, we pass the appropriate starting coordinates and the new size, which is half. Once the subregions are processed, we create an internal node. This internal node is not a leaf, so isLeaf is set to false, and its 4 child pointers are assigned to the respective subregion nodes. This allows us to represent the non-uniform region as a combination of its smaller, uniform subregions. Finally, we return to the main construct method. Here, we calculate the size of the grid, n, and initiate the recursive process by calling buildQuadTree with the entire grid, starting from the top left corner, 0, 0, and using the full grid size. This results in the construction of the complete quad tree, which is then returned as the output of the method. Here, we begin by defining the node class, which represents the structure of each node in our quad tree. Each node has 2 main properties, val, which indicates the value of the node, and isLeaf, which tells us whether the node is a leaf node or not. Additionally, it contains 4 references, top left, and bottom right, which point to the child nodes of the current node. We provide 3 constructors for flexibility. The first is a no-argument constructor, the second allows us to set the value in leaf status, and the third allows us to initialize a node with its value, leaf status, and all 4 child nodes. This forms the backbone of the quad tree structure, enabling us to represent both leaf nodes and internal nodes that have children. Next, we define the construct method, which serves as the starting point for building the quad tree. It takes a 2D grid as input and calls the helper method buildQuadTree, starting from the top left corner of the grid and including the entire grid size. To support this process, we also define the isUniform method. This helper function checks whether all the values in a specific square subgrid are the same. It does so by iterating through the subgrid, starting from the top left corner, and comparing each value to the first value in that subgrid. If any value differs, it returns false, otherwise, it returns true. This is crucial for determining whether a subgrid can be represented as a single leaf node in the quad tree. Finally, we complete the buildQuadTree method, which is a recursive function that constructs the quad tree. If the size of the current subgrid is 1, we create and return a leaf node, where the value is determined by the grid cell. If the subgrid is uniform, as determined by the isUniform method, we also create a leaf node with the appropriate value. Otherwise, we divide the current subgrid into 4 equal parts by halving the size. We then recursively call buildQuadTree for each quadrant, top left, and bottom right. After constructing nodes for all 4 quadrants, we create an internal node, setting its isLeaf property to false and linking the 4 child nodes. This process ensures the quad tree is built by decomposing the grid into smaller parts until each part can be represented efficiently. In this example, we have a 2x2 grid where all the values are 1. The function construct begins execution, and since the grid size is 2, we call the helper function build quad tree with the coordinates 0, 0, and size 2. This means we are analyzing the entire grid. To determine if the grid is uniform, we call isUniform with the same parameters. IsUniform iterates through every cell in the grid and finds that all values are indeed 1. Therefore, it concludes that the grid is uniform and returns true along with the value 1. Based on this, we create a leaf node with val equals true and isLeaf equals true, representing the uniform grid. The final quad tree here is simply a single leaf node with a value of true. Now, let's analyze a 2x2 grid where the values are not uniform. The grid contains 1 in 3 cells, but the bottom right cell has a value of 0. The function construct starts, and we call build quad tree with the entire grid. IsUniform checks if all values are the same by iterating through the grid and finds both 1 and 0. Since the values are mixed, isUniform returns false. This prompts us to divide the grid into 4 smaller quadrants, each 1 by 1 in size. For the top left quadrant, we call build quad tree and find it contains a single value of 1, so we create a leaf node with val equals true. Similarly, the top right and bottom left quadrants also contain only 1, so we create leaf nodes with val equals true for each. Finally, the bottom right quadrant contains 0, so we create a leaf node with val equals false. These 4 leaf nodes represent the individual values in the grid. After creating the 4 leaf nodes for the quadrants, we combine them into a single internal node to represent the entire grid. This internal node has val equals true to reflect that the majority of the grid contains 1, and isLeaf equals false because it is not a uniform grid. The internal node has 4 children, the top left, top right, and bottom left nodes, which all have val equals true, and the bottom right node, which has val equals false. This internal node becomes the root of the quad tree. Moving on to a larger example, we now consider a 4x4 grid. The function construct starts, and build quad tree is called with the entire grid size of 4. In this larger grid, isUniform is called to determine if the grid is uniform, but it finds mixed values, so it returns false. This leads to splitting the grid into 4 2x2 quadrants. For the top left quadrant, isUniform finds that all values are 1, so we create a leaf node with val equals true. For the top right quadrant, all values are 0, so we create a leaf node with val equals false. Similarly, the bottom left quadrant contains only 0, which results in another leaf node with val equals false. Finally, the bottom right quadrant contains only 1, so we create a leaf node with val equals true. These 4 leaf nodes are then combined into an internal node, which has val equals true and isLeaf equals false. This internal node becomes the root of the quad tree, representing the entire grid. The final quad tree has 1 internal root node and 4 leaf nodes, 2 with val equals true and 2 with val equals false. To analyze the time complexity of constructing a quad tree, we must focus on the 2 key functions, isUniform and build quad tree. The isUniform function determines if all elements in a given subgrid are the same, either all zeros or all ones. This requires iterating through every element in the subgrid, which, for a grid of size x size, involves size(2) operations. The worst-case scenario arises when no subgrid is uniform, forcing isUniform to be called repeatedly at every level of recursion. Meanwhile, the build quad tree function works recursively by dividing the grid into 4 equal quadrants at each step. For a grid of size nxn, the first level performs an isUniform check on the entire grid, which takes n squared. If the grid is not uniform, it recurses into 4 smaller subgrids, each of size n/2, x, n/2. This recursion continues, having the grid size at each level, until the base case, where the grid size is 1. At each level, the total work done is proportional to the number of cells being processed, which remains constant across all levels of recursion as it reflects the total number of grid cells. When we calculate the total time complexity, we observe that the grid is divided into 4 smaller subproblems at each level of recursion, and there are log n levels since the grid size halves at each step. At each level, the total work done by the isUniform function is proportional to n squared, as it processes all cells exactly once across all recursive calls. Combining these observations, the overall time complexity for constructing the quad tree is O(n squared). For space complexity, we consider two factors, the recursion stack space and the storage used for quad tree nodes. The recursion depth corresponds to the levels of the quad tree, which is log n, for a grid of size nxn, as the grid is halved at each level. Since each recursive call uses O(1) space, the recursion stack space totals O log n. The second component of space complexity is the storage required for the quad tree nodes. In the worst case, where every cell in the grid must be represented as an individual leaf node, there will be n-2 nodes, one for each cell. In contrast, the best case occurs when the entire grid is uniform, requiring only a single node to represent the entire structure. Therefore, the space required for the quad tree nodes ranges from O(1) in the best case to O(n squared) in the worst case. Combining this with the recursion stack space, the total space complexity is also dominated by the O(n squared) term in the worst case. Analyzing the best, average, and worst cases for constructing the quad tree reveals further insights. In the best case, where the grid is completely uniform, the isUniform function completes after a single check, and no further recursion is required. The time complexity in this scenario is O(n squared) due to the initial uniformity check, while the space complexity is minimal, requiring only O(1) for the recursion in the single node. In the worst case, where the grid has no uniform subgrids, the recursion reaches its maximum depth, and isUniform is invoked for all subgrids at each level. This results in both time complexity and space complexity being O(n squared), as the maximum number of nodes in total grid processing occur in this scenario. Comparing the quad tree approach to a naive method provides additional context. A naive approach stores the entire nxn grid as is, requiring O(n squared) space but lacking the efficiency of hierarchical representation. The quad tree optimizes space in cases where the grid has large uniform regions, significantly reducing the number of nodes needed. However, in highly non-uniform grids, the time and space complexity of the quad tree approach matches that of the naive method, both being O(n squared). To mathematically confirm the time complexity, we note that the number of recursive calls in build quad tree follows a geometric sequence, 1 for the root, for at the next level, 16 for the level after, and so on, up to 4 to the power of k, where k equals log n. The sum of this sequence is proportional to the total number of cells in the grid, which is O(n squared). For space, the worst-case scenario involves n-2 nodes, 1 per cell, along with an O log n recursion stack. This confirms that the space complexity is also dominated by O(n squared) in the worst case. One of the most common mistakes when working with quad trees is not properly handling non-uniform regions. This happens when developers assume that every subgrid is a leaf node without actually verifying if all elements in that region are the same. To prevent this, it's crucial to implement a helper function that checks whether a region is entirely filled with zeros or ones before creating a leaf node. Another frequent issue is inefficient recursion when processing large grids. Without strategies like memoization or early stopping, you may end up performing redundant calculations. For example, if a region is already confirmed as uniform, there's no need to divide it further, returning immediately saves significant computation time. Lastly, an incorrect base case in recursion can cause problems. If the base case for single-element grids, such as a 1x1 region, is not explicitly defined, the algorithm might fail. The solution is to specifically handle these smallest regions and ensure leaf nodes are created correctly for them. Another mistake to watch out for is misunderstanding the quad tree structure itself. A common error is confusing leaf nodes with internal nodes, which can lead to an improperly constructed tree. To avoid this, remember that the isLeaf property should only be set to true for regions that are completely uniform. Additionally, indexing errors can arise when dividing grids into subregions. Miscalculating the row and column ranges during the divide step can result in incorrect subgrids, breaking the algorithm. This often happens due to overly complex logic or incorrect offset calculations. The solution is to carefully design and test the grid splitting logic to ensure the 4 subgrids are correctly computed. When it comes to interviews, there are a few key insights to keep in mind. First, quad trees are fundamentally a divide and conquer problem. You should be able to clearly explain how your solution recursively splits the grid into smaller regions and merges the results. Efficiency is another critical aspect. Be prepared to justify how your approach avoids redundant processing, such as skipping uniform regions to save time. It's also important to address edge cases, like handling one-by-one grids or grids that are entirely filled with zeros or ones. These scenarios often come up in interviews, so demonstrating that your solution accounts for them will leave a strong impression. Lastly, interviewers may ask about space complexity, especially due to recursion. You should be ready to analyze how the depth of the recursion tree impacts memory usage and explain any trade-offs involved. To deepen your understanding of quad trees, it can be helpful to explore related problems on LeetCode. For instance, problem 116, populating next right pointers in each node, involves similar principles of tree construction, although it deals with binary trees instead of quad trees. Problem 100, same tree, is a great way to practice validating tree structures and recursive traversals. Another useful problem is 226, invert binary tree, which focuses on tree manipulation through recursion. Finally, problem 130, surrounded regions, deals with grid-based recursion and can improve your skills in processing 2D grids, which is highly relevant to quad tree construction. There are also alternative approaches to constructing quad trees. One rare but possible method is using an iterative approach where you simulate the recursion stack manually to process regions. While this avoids recursion depth limitations, it can make the code significantly more complex. Another variation is choosing between top-down and bottom-up construction. In a top-down approach, you start with the entire grid and recursively divide it into smaller regions. Conversely, a bottom-up approach begins with individual one-by-one grids and merges them upward. Top-down is more intuitive but might be less efficient for sparse grids, whereas bottom-up can save time in specific cases. Finally, a memoized approach allows you to cache results for previously computed subgrids, reducing redundant computations. However, this comes with the trade-off of increased memory usage, so it's important to weigh the benefits against the costs depending on the problem's constraints. Great job! Today, we learned how to construct a quad tree from a 2D grid using recursion. This problem emphasized the power of tree structures for hierarchical data representation. Keep practicing similar problems to strengthen your skills. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!